Now we'll discuss the Z transform of a signal. How we can find the Z transform of a signal. X of n is equal to a raised to n into e of n. And in order to calculate the Z transform, we need to use the general formula as x of Z is equal to sigma n is equal to minus infinity to infinity x of n into Z raised to minus n. So this is the general formula. Now in place of x of n we need to substitute this equation a raised to n into e of n, and now we can see that what is e of n. E of n is a standard signal, it's a standard step signal. This u of n is equal to 1 for n greater than or equal to 0 and 0 for n less than 0. So if you plot the waveform, you can see that u of n is having non-zero magnitude from 0 to infinity, and you are multiplying that signal with z raised to minus n. So instead of calculating the summation from minus infinity to infinity, we can calculate or we can change the limit x of z is equal to sigma n is equal to 0 to infinity, and in place of x of n you can write a raised to n into 1, because from n is equal to 0 to infinity, u of n is equal to 1, and for minus infinity to minus 1, so minus infinity to minus 1 the function magnitude is 0, so we need to write only from 0 to infinity 1 into z raised to minus n. So if you rearrange this, you can see that it's n is equal to 0 to infinity a z raised to minus 1 the whole raised to n. Now we can apply the summation formula. So this is the general formula to evaluate the summation. If it is n is equal to 0 to infinity k raised to n, you can write 1 by 1 minus k, provided this modulus of k is less than 1. So we can assume that this a is raised to minus 1. In place of k, here it is given a is raised to minus 1. So I can apply this limit. So I can write 1 by 1 minus a is raised to minus 1, provided this condition is satisfied. So I can write in place of k, it is written as a modulus of z, a is raised to minus 1. So I can write a is raised to minus 1 should be less than 1, or this is raised to minus 1 I can rearrange modulus of a divided by modulus of z should be less than 1, or I can say that modulus of a less than modulus of z, or in terms of modulus of z I can say modulus of z should be greater than modulus of z. So this equation is valid, or Z transform exists only for this particular range of values of z. So this is known as the ROC, a region of convergence of this particular Z transform. I can also write this Z transform if you take this z raised to minus 1, and I can write it becomes z by z minus a, and the ROC, region of convergence, can write modulus of z greater than modulus of a. And graphically I need to show this waveform. So I can consider the z is equal to the numerator z and the denominator is z minus a. So if we keep the numerator equal to 0, that is known as zeros. So you will get a 0 at this point. So this is 0. And if you equate the denominator z is equal to minus a, then z becomes a. So you can write assume that this is the point a. So this is a pole and this is 0. So you can say this is known as 0 and this is pole. This is pole. And modulus of z means in the z plane, you got a pole which is z is equal to a, and modulus of z means z is a complex number, so z is a complex number and it is defined as r e raised to j omega, and if you take the modulus of this, you will get modulus of r into modulus of e raised to j omega, and this modulus of e raised to j omega is equal to 1, so simply you will get it becomes modulus of r, means this actually represent a circle whose radius is a. So this is a circle whose radius is a. Okay, in the z plane, this is a circle with a radius a, and you can see that the ROC or region of convergence, or this result is valid only when modulus of z is greater than a, and you can mark this region of convergence. This is a circle with modulus of z is equal to a, and here it is modulus of z greater than a, so you can indicate the region outside this circle. Outside this circle is known as the ROC, a region of convergence, or this result is valid only in this particular region, ROC modulus of z greater than a, or graphically I can say this is the ROC region. And from this you can see that ROC, when z is equal to a, what happens? It becomes 0 and the result is going to infinity. So ROC never contain a pole. So this is one point you should remember. ROC does not contain any pole because is not equal to a, is greater than a. So ROC does not contain any pole. This is a point you should remember, and we will discuss one more point, and here about the region of convergence. Okay, here the region of convergence is exterior to the circle, exterior of the circle, modulus of z is equal to r. Here in place of r you can write it's equal to a. So in this particular case, ROC is the exterior of the circle. So this is a circle modulus of this is a circle which indicating modulus of z is equal to r in general, or we can say in this particular example it's a, and this is a circle, and exterior of the circle means the shaded portion, that's a ROC. Now we will discuss another question. Find the Z transform and ROC of the signal x of n is equal to minus b raised to n into u of minus n minus 1. And in order to calculate the Z transform, we need to use the general formula, which is x of z is equal to n is equal to minus infinity infinity x of n is raised to minus. In place of x of n, we need to substitute this. So there is a signal which is given by u of minus n minus 1. So we need to check what is the u of minus n minus 1. So it's a step signal, so I can write like this: u of minus n minus 1 is equal to 1 for the limit minus n minus 1 greater than or equal to 0, just like a step signal. Okay, in place of n, here it is written minus n minus 1, so you can write minus n minus 1 should be greater than or equal to 0, and if you rearrange this, minus n greater than or equal to 1, or if you multiply with minus 1, it becomes n and minus 1, so we need to change this. So we got this signal is having the magnitude 1 when n less than or equal to minus 1, and other case is 0, so we can write n greater than minus 1. So we can see the waveform. So this is the waveform, and you can see that from 0 onwards, because n greater than minus 1 means next point is 0, so 0 to infinity the function magnitude is 0. Okay, and for other value from, so that is n is less than or equal to minus 1, so this is a point minus 1 and less than minus 1, so all these regions the function magnitude is 1. Okay, so I can change this limit and I can write the equation x of z is equal to sigma, this function magnitude is 1 from minus infinity to minus 1, this region. So we need to start from minus infinity. So you can write is from minus infinity to minus 1. Up to minus 1 the function magnitude is 1, otherwise 0. So into minus b raised to n into z raised to minus n. So we got the equation. Now we can rearrange this equation. So I need to change this minus to plus. So you can simply write the summation becomes n is equal to 1 to infinity. So there is a minus. You can write minus this minus. Okay, I can write here. Then in order to change this limit to positive, I need to change the internal n value. So if you are making this limit to positive, the variable n should be minus. So I can write like this. It becomes b raised to minus n and z raised to n. You can see the difference. Okay, if you are changing this from minus infinity and minus 1, now I am changing to 1 and infinity. So initially it is n and minus n, now it is minus n and n. So you will get the same result. So I can group it minus n is equal to 1 to infinity b raised to minus 1 z the whole raised to n. Now we can see that this limit is from 1 to infinity, so we need to use the summation formula. Not n is equal to 0, now it is starting from n is equal to 1. Here in place of m it is 1, so m to infinity k raised to n is k raised to m by 1 minus k, provided the modulus of k is less than 1. So in place of k it is b raised to minus 1 into z, and in place of m it is 1. So you need to remember this formula. So I can write x of z is equal to minus b raised to minus 1 z the whole raised to 1 divided by 1 minus b raised to minus 1 z. Okay, and if you take this b raised to minus 1 z is common, and one more case I need to write this condition also, that is b raised to minus 1 z should be less than 1. And next case, if you take this b raised to minus 1 z as a common from both numerator and denominator, and you can write as minus 1 by okay 1 by b raised to minus 1 z minus 1. And again I can write, if you multiply with this, I can write 1 by 1 minus b z raised to minus 1. We are multiplying with this minus, and taking b raised to minus 1 becomes b, and z becomes z raised to minus 1, and we are multiplying with minus, so you will get this. And the condition is modulus of z by modulus of b less than 1. Or if you rearrange this, okay, if you take this z raised to minus 1, then it becomes z by z minus b. And in the ROC, region of convergence, you can write modulus of z less than modulus of b. So we got z by z minus b, ROC, modulus of z less than modulus of b. Okay, now we can see the ROC in graphical way. So here you can see this is the z plane, and this is the real axis and the imaginary axis, because z is a complex number. And here you can see that z, if you equate the numerator equal to 0, so numerator equal to 0, you will get z is equal to 0. So your ROC in the z plane, you can mark this is a 0. Okay, and this is a 0. And if you equate the denominator, b minus z minus b equal to 0, you will get the pole is b. So b is the pole. So this is a pole. I got the pole. Okay. Now modulus of z. Modulus of z is less than modulus of b. So modulus of z means as a circle and whose radius is b. That's the meaning. So I can plot a circle, and here it is z is less than b. So means this is the shaded portion inside the circle. So this is the ROC. And again you can see that if z is equal to b, again the function magnitude is infinity. So this pole does not contain in the ROC region. So it's not equal, it's less than b. So I can conclude 2 points. ROC does not contain any pole. Okay, that point is valid. And another point, the ROC is interior of the circle. Modulus of z is equal to r. In this case, that value is b, or modulus of b. Okay, so we will get the same result, z by z minus b, and modulus of z is less than modulus of b, and the ROC is different. Okay, now we will compare the last two questions. That is x of n is equal to a raised to n into u of n, and the second question a raised to n into minus a raised to n into u of minus n minus 1. You can see the answer. The first question, the answer x of z is equal to z by z minus a, and the region of convergence is given by modulus of z is greater than modulus of a. In the second question, again we got the same answer, x of z by z minus a, and the ROC you can see that it's modulus of z less than b, sorry, it's a. In this case it's a. The only difference that in the previous question instead of b, in this case we are writing a. That's only difference. So you can see that in both cases you are getting the same answer, but the question is different. Here it is a raised to n into u of n, and here it is minus a raised to n into u of minus n minus 1. And you can see that the ROC, here it is modulus of z greater than modulus of a, means the ROC is in the z plane. You can mark that it's exterior to the circle. Okay, it's exterior to the circle, and in the second case you are getting the same answer, z by z minus a, and the ROC is less than modulus of z less than modulus of a, means interior of the circle. That's the only difference. And in other way you can say that in this question, this a raised to n into u of n, this u of n is actually a causal signal. Okay, so this is a main point you should remember, means the signal is in the time domain, it is in the positive side, because there is a u of n signal which is in the exists only in the positive part. And here you can see that is u of minus n minus 1, which you can write is an anti-causal signal. Okay, it's an anti-causal signal, meaning it's only in the negative side. So in both question, it's a standard question, you need to remember the result. Here the question is a raised to n into u of n, you will get the same answer, z by z minus a. Here the question is minus a raised to n into u of minus n minus 1. In both cases you are getting the same answer, but the ROC is different, because one signal is a causal signal and another signal is anti-causal signal. You need to remember this question and the ROC, because we need to use this result when you find the inverse DTFT, sorry, inverse is a transform. Okay. Now we'll see another question, which is a combination of two signals, a raised to n into u of n and b raised to n into u of minus n minus 1. We can take these two signals, or we can consider these two signals as separate signal. For example, this is x1 of n, you can consider. This is another signal which is x2 of n. So from the previous result you can say that the z transform of x1 of z, or the first signal transform, you can write z by z minus a, and the modulus of z is greater than a, you can consider the ROC of the signal if it is only x1 of z. So this is the ROC, region of convergence. And you can take the second signal which is given by x2 of z. Okay, x2 of z can be written as z by z minus b, and modulus of z less than modulus of b. Okay, so we got and this is the ROC of the second signal, region of convergence. Now we got is a transform of two signals. From the previous two examples we know the result, z by z minus a, and okay, and now in this question it is asked x of n is equal to the sum of these two signals. So in general case we will write the sum of these two, but here we need to check one more condition, that is we need to check the combined ROC. Okay, so here we need to take two cases, because in this case, in the first case you can see that there are two variable. If you want to combine this, one is z is greater than a. So in the first case you can see that there is a pole which is written by a. Okay, and another case which is written as b, modulus of z less than b. So I can mark 2 points. Assume that in this case a is here and b, because we don't know the values of a and b, so I need to take two cases. One case is modulus of a and less than modulus of b. So this is the first case we need to consider. Another case we need to consider modulus of b and modulus of a is greater than. Okay, now we will take the first case, a is less than b. Okay, and you can construct two circles here. One, a circle with radius a. Okay, we got one circle. Another circle with radius b. So we got two signals, two circles. One is z is equal to a and z is equal to b, and you can see that one case is modulus of z is greater than a. So this is a. Okay, and the circle a, and it is greater than a, means exterior to the circle. So this is the region of convergence of the first signal. Okay, is x1 of z. And the second case, it is given modulus of z less than b. So again I can see that this is the point b and is less than b, so means interior. Okay, so one is exterior and other one is interior to the circle. Okay, you can mark like this. So one is greater than a, other one is less than b. So you can see that there is a common area, and the common area is from a to b. So because one signal is greater than a and another signal is less than b, so if you combine these two signal, there is a common area, overlapping area. So there is a ROC's overlap. So I can say that the combined ROC is modulus of a less than modulus of z less than modulus of b. So we got the common area. So I can write x of z is equal to z by z minus a plus z by z minus b, and the ROC is the strip, which is a common area of these two signals. And now we can see another option, that is modulus of a is greater than b, means you need to mark a here, b and a, because a is greater than b. So again I need to construct two circles, one is with radius b and another one is with radius a. And you can say the first case, modulus of z greater than a, means outside the circle. Okay, and the second case, modulus of z less than b, means interior of the circle. Okay, this is the region, and you can see that there is no common area in this particular case. So there is no overlapping, no overlap in the ROCs. So if you take the ROCs, there is no overlap. So x of z does not exist. Okay. So individually is a transform exists, but the combination is a transform does not exist. But here the is a transform exists because there is a common area for the two signals. So that in that region only this a transform exists, and here there is no common area or overlapping area. So x of z does not exist. So very important question. When you evaluate this transform, always remember you need to take care of this ROC. Okay, if it is an individual signal, okay, it exists. X1 of z exists, x2 of z, x2 of z also exists, but the combination exists only when modulus of a less than b, because there is only common area. So always we need to check is there any common area, otherwise is a transform does not exist.